Today we are going to find the Fourier transform of a really interesting function called the two-sided exponential. Alright, so our main goal is to find the Fourier transform which we call f of omega for our function f of x. If you look at the graph, you can see exactly what this function looks like. It has a sharp peak right at the origin and then decays symmetrically on both sides, creating a really distinctive shape. Let's dive in and see what its Fourier transform looks like. Let's start with the standard definition of the Fourier transform. F of omega is given by the integral from negative infinity to positive infinity of our function f of x multiplied by e to the power of negative iota omega x dx. So the first thing we'll do is substitute our specific function into this formula. This gives us the integral we need to solve f of omega equals the integral from negative infinity to positive infinity of e to the power of negative a times the absolute value of x times e to the power of negative iota omega x dx. The key to solving this integral is dealing with that absolute value of x. Remember, the absolute value function is a piecewise function. It's equal to x when x is greater than or equal to 0, but it's equal to negative x when x is less than 0. Because of this, we need to split our single integral into two separate parts, right at x equals 0. The first integral will go from negative infinity up to 0, and the second one will go from 0 to positive infinity. This gives us f of omega equals the integral from negative infinity to 0 of e to the power of negative a times negative x, multiplied by e to the power of negative iota omega x dx plus the integral from 0 to positive infinity of e to the power of negative ex times e to the power of negative iota omega x dx. Now that we've split the integral, our next step is to simplify the exponents in each part by combining the e terms. Let's start with the first integral, which covers the domain where x is less than 0. Here we have e to the power of x times e to the power of negative iota omega x. Combining these gives us the integral from negative infinity to 0 of e to the power of the quantity a minus iota omega all times x dx. Next, for the second integral where x is greater than or equal to 0, we have e to the power of negative ax times e to the power of negative iota omega x. Combining these gives us the integral from 0 to positive infinity of e to the power of negative, the quantity a plus iota omega all times x dx. As you can see in the diagram, this split is visually represented by dividing the area under our function into two parts. The red shaded area on the left corresponds to our first integral, and the blue shaded area on the right represents the second. This makes it really clear what we're working on. Okay, let's evaluate the first integral, the one for the negative domain. The integral of e to the power of the quantity a minus iota omega times x is simply that same exponential divided by the constant a minus iota omega. We'll evaluate this from negative infinity to 0. Plugging in the upper limit of 0 gives us e to the power of 0, which is just 1 over a minus iota omega. For the lower limit, as x approaches negative infinity, the e to the ax term goes to 0 because a is positive, so the entire second term disappears. This leaves us with a very simple result for our first integral, 1 over a minus iota omega. Now let's do the same thing for the second integral, which covers the positive domain. The integral of e to the power of negative, the quantity a plus iota omega times x, is that exponential divided by negative the quantity a plus iota omega, and we evaluate this from 0 to infinity. This time when we plug in the upper limit of infinity, the e to the negative ax term goes to 0. So our first term is 0. Then we subtract the value at the lower limit of 0. Plugging in 0 gives us 1 over negative a plus iota omega. So we have 0 minus a negative value, which makes it positive. The result for our second integral is 1 over a plus iota omega. We are in the home stretch. All we have to do now is add the results from our two integrals to get the final Fourier transform f of omega. So we have f of omega equals 1 over a minus iota omega plus 1 over a plus iota omega. To combine these, we'll find a common denominator, which is just the two denominators multiplied together. This gives us a plus iota omega plus a minus iota omega in the numerator all over the product of a minus iota omega and a plus iota omega. In the numerator, the iota omega terms cancel out, leaving us with just 2a. In the denominator, we have a difference of squares, which gives us a squared minus the quantity iota omega squared. And since iota squared is negative 1, the denominator simplifies to a squared plus omega squared. And there we have it. F of omega is equal to 2a over a squared plus omega squared. So let's recap our final answer. The Fourier transform of the two-sided exponential function f of x equals e to the power of negative a times the absolute value of x is f of omega equals 2a over the quantity a squared plus omega squared. Looking at the figure, you can see this beautiful relationship visually. On the left, our original function has a sharp cusp at the origin. But after we apply the Fourier transform, we get the function on the right, a smooth bell-shaped curve. It's a fantastic example of how a sharp feature in one domain transforms into a smooth spread-out feature in the other.